Good morning, students. So, in the last class, we have finished that is the properties of the fluid. Today, I am going to start the pressure. Let us see that. First, you just tell me. So, see, first, you just tell me what is difference between the pressure and stress. Anybody just come forward and tell me pressure and stress. Just tell me what is difference between the pressure and stress. Both are that is the pressure per unit area. Am I right or not? Hello.
Sir, pressure is external while stress is internal.
Pressure is
External while
okay.
stress is internal.
Or any more difference?
Pressure is vector, a scalar, and stress is tensor.
That is the intenser. And what about the direction of the pressure and stress? Pressure is acting inwards. Stress is always acting outwards. Am I right? What is the reason for the stress? Why stress forces are acting? Just tell me. That is the
Internal resistance.
Internal
that is
resistance.
the yes. Anybody? Yes. That is the viscous. That is the viscosity. That is the basic reason is viscosity. Am I right? That is the basic reason. So let us see. Just I am going to introduce. Is it visible?
Yes,
Okay,
yes,
thank you.
sir.
Yes. So just I am going to the pressure. So pressure is actually in mathematically or that is the scientifically it is represented by the dFy dA, where dA tends to 0, means area will become a point, then acting that the unit force on the point that will give a pressure, and that is the obviously it is the unit is the Newton per square meter or Pascal. It is always acting inwards, always, and normal force that is the so so that is the pressure transmission. So Pascal's law in a closed system, there are types of the system you might read in the thermodynamics. One is the closed system, another one is the open system. Here that is the we are discussing that is the closed system. So pressure change produced at one point in the system is transmitted throughout the entire system. Whatever may be system, whatever may be the size, may be circular, may be cylindrical, may be spherical, or may be rectangular, doesn't matter, but it will transmit throughout the entire system what we have taken or assumed. Then there are some pressures that is sometimes we are talking about the pressures is the vacuum or higher pressure. So here when that is the pressure that is absolute atmospheric pressure, you might be know it is exactly that is the 101.325 kilopascal. And we will consider when pressure at any point is greater than a atmospheric pressure, then gauge pressure difference is positive. If it is the less, then we are talking about the vacuum pressures. Let us generalize the pressure considering the wedge shape. That is the in generalized case we have chosen, so we can apply any shape. That's why. So see that this is the fluid element of the wedge shapes. This is the fluid. We are considering a fluid element of the wedge. That is the wedge shape. And different types of the forces acting on this, that is the shape, are shown. That is the here. See the first one, that is the axis is also marked, that is the vertical z, that is the x-axis, and that is the y. All that is. So see that is the del A geometry, that is the del A, capital A, del X, del Z, where that is the mention L, that is the length of the our wedge inclined plane, that is the length is given, del A is area is given, then how much, that is the forces acting along the x-axis, summation of, it is the hydrostatic, it is not moving with any acceleration, it is the still, it is the static. So that's why sometimes we are analyzing such situations is called hydrostatic pressure. So summation of forces equal to the zero. There is a no any acceleration, no motion, no any movements. This what type of the forces acting along the x direction of this shape Pn. So here that is the shown, that is the Pn normal force on the inclined plane into area. Pressure is always acting that is the norm, and area that will the change del n a sine alpha. Alpha is nothing but inclination of the plane or wedge with reference to the x-axis, and then that is the, so this when you resolve it, that is the comma minus px. So acting that is the along x-axis, as I told you, pressure always acting inwards, and along the x-axis it is the positive but acting inward towards opposite of the x-axis, so minus px into del a sine alpha equal to 0. So Pn that is the pressure on the normal pressure on the inclined plane equal to the pressure acting along the x-axis. Mass, that is the weight of this element, m into g, and generally in the fluid mechanics we will transfer the mass in the term of the density by using the volume. And here average, that is the this average, that is the half del x del y del z is the volume. So then next component, that is the fz, that is the vertical direction, minus pn del ly cos alpha plus pz del l del y cos alpha, this equal to, and minus that is the w is acting downward, and Pn is out acting that is the downward, so this is, that's why minus Pz is acting upward plus, and that will give you relations that will come out finally, Pn equal to the Px equal to the Py and Pj, when del L means this inclined length tends to 0, means at a point. All these are, so P is a single value at a point and independent of direction, that is the alpha arbitrary and independent Pn of alpha. So this, that's why P is a scalar and isotropic. And isotropic, it will change with this sign. So for that is the basic differential equations, pressure variation with elevations. So see here, that is the a fluid element of the length dx, dy and dz. A fluid element are shown perhaps x, y and z, three axes, and its corresponding fluid element length is dx, dy and dz. And on this, that is the fluid element, the forces acting are given by the arrow mark. You should always remember here the bottom surface is, that is our starting for the z axis, and top section on the height of the dz. So lower pressure is acting in the lower face, whose length is dx, dy, and pressure acting is p, and pressure force on the bottom surface is acting p into the area of the fluid element on the bottom is dx, dy. On the top, it is also acting towards the fluid element. It means lower force acting upward, upward force acting the downward. So due to the fluid element length dz, the upper pressure will change, and this equation is written from the Taylor series. So Taylor series up to the 1 plus term, then you should go higher term p plus del py del z into dz into area. So here Taylor series, when you should expand p plus del py del z into dz plus del 2 py dz square into dzy factorial t, like that, that is the so on it go. But here the higher order term is eliminated. That's why it is written only two terms. P plus del py del z into dz. This is the pressure change from bottom to top into area dx into dy. This acting the downward on the fluid element. G is also acting on this fluid element is downward. So that is the W is rho into G means mg. Mg will become rho into dx, dy, dz into G. So all these are the here on the our free body diagram. It is written. So this is also we are analyzing for the hydrostatic situations. For the stationary fluid element, we are not discussing any movement of this system or this fluid element. So summation of the forces, Newton's second law, that is according to that. Summation of forces equal to the mass into acceleration. For a static zero, summation of forces x-axis, y-axis and z-axis equal to 0, because in all direction it is the static, no movement. So here z direction is upward, so this p into dx dy acting from the bottom, and from the top minus p plus del py del z into dz. Always remember this term is written from the Taylor series and due to the change in the height dz. That's why it is a divide and multiply into the area minus. We are taking the upward, that is the fz equal to 0, upward force. So downward is gravity minus rho g dx dy dz equal to 0. Or we can say del py del z equal to the minus rho g, or nothing, a specific weight, that is the minus gamma del py del z. If z is upward axis, vertical axis, if it is a y, then it will become del py del y equal to the minus rho g or minus gamma. Some book may be used y, some book may be used z, but it is the vertical direction, always remember. So del py del z is minus rho g. So here see z is vertical direction or height. This is the elevation. This is the relations between the pressure and the elevation. So basic equation for the pressure variation with elevation. So del y, del the summation of force, y direction, x direction, nothing. So all these gradients will come out the zero. Finally, the elevation or upward or vertical only the relation del Py, the del Z minus rho G means this pressure gradient is developed due to the gravity and depends on the density of the field. High density, high gradient, low. So for a static fluid, the pressure only varies with elevation Z means vertical height and is constant in horizontal xy plane. So the basic equation for the pressure variation with elevation can be integrated and rho, let us suppose rho is a constant, so whether the fluid is incompressible or compressible, then C is also constant. So that is our here another pressure variation for uniform density. So see, when we are interested to the find out the pressure, then we can integrate P equal to the minus gamma or minus rho g into dz. Heat variations or height may be given. So then we can find out the pressure at any height, any depth. So let us see here, that is the pressure variation for throughout the uniform density of the fluid. So here the distribution of the pressure is shown as pressure is a function of Z. Pressure is a function of the elevation. Pressure is a function of the height. So obviously the distribution that is here given at the surface, that is the acting, that is the less at the bottom due to the fluid height acting more and more as we go the inside, pressure is acting more and more because more layer of the fluid is available. So del P by del Z equal to the minus gamma or del P equal to the minus gamma del Z, then pressure difference at the final point to the initial point is equal to the minus rho g final height divided minus initial, or you should take plus, then it will become reverse, initial to final. But it is always remember del Py del Z, del Py del Y equal to the minus rho g this time. Or that is the you may apply the P1 plus gamma Z1 equal to the P2 plus gamma Z2 is constant. Or this P plus rho G Z, rho G H, if gamma Z is actual height is yes, this is the constant. Pressure plus rho G H, pressure is nothing, rho G H always both summation, that is the actual pressure plus piezometric height or the column height, that is the P equal to the gamma Z is called piezometric pressure. Always this is the summation of both P del P equal to the gamma Z means Z is the height of the fluid plus the how much pressure is acting, that will give the piezometric pressure. When you should write down in the head form, nothing p is divided by rho g, then it will come in the head form. It is also sometimes called piezometric head. See here, that is the given Py, the gamma plus Z is constant. This is called piezometric head. So when we should use barometer, manometer, then we will use generally piezometric head. But in pressure, we can also transform. So pressure either may be right in the absolute pressure in the or in the head form. Meter of the water, meter of the mercury, like that, or Pascal. So these are the relations. Then press next, that is the this is a piezometric height. Then come on, that is the pressure distribution in a fluid. That is the arbitrary fluid we have chosen here, and this portion of the control volume fluid element is taken, and control volume is formed by the control surfaces such as that is we can take a square, rectangle, or cubic or cuboid. Then each surface will become called control surface, and whole system is called control volume. So so then the forces we have chosen a small fluid element of the area daily, and a unit word, a unit vector out normal word, that is the n, and any arbitrary force is acting d, but n is the that is the unit vector outward. So the body force act on the entire body of the fluid, and surface force act as the control surface and are due to the surrounding medium, force per unit area or stress. Again, see, body force acting on the entire body means M into G, that is the force per unit volume. We will transfer, that is the mass into the density into volume, then density and per unit volume, then rho into G, that is the body force for the any system. But surface forces acting are the difference, tangential, normal, all these are. So at the force, surface forces act at the control surface and are due to the surrounding medium or force per unit area, that is the stress. Force per unit area is pressure also. So normal force acting both, that is the pressure and stress, and shear stress acting on this plane is only a shear force. So in generally here, that is the shown you, that is the fluid element of the dx, dy, dz is the its length, and x, y, z coordinate system of the shown cubical fluid element. So sigma xx, sigma xy, sigma xz. So stresses acting on the axis, along the axis x, and normal to the x-axis, that will become sigma xx. Normal to the y, sigma xy. Normal to the z, sigma xz. Acting the stress along the x-axis, first subsuffix, then acting the perpendicular to the x-axis, second acting perpendicular to the y, sigma xy acting perpendicular to the z, but acting along x, and acting along x, its effect along the or perpendicular to the y-axis, y perpendicular to the z, we are interested. That creates the stresses. So then sigma, when we should write sigma, that is the matrix sigma xx, sigma xy, sigma xz. Similarly for the y phase, similarly for the y axis, and Z axis we can write. So these are the representation of the stresses, and it is not sure ki sub suffix always give that is the first axis, in which axis or in which direction it is acting. In different books may be used first that is on surface, which surface it is acting. But in this that is the note, first is the subsuffix we have represented along the direction in which the stress is acting. So fluid cannot withstand shear stress. See, the fluid cannot withstand a shear stress without moving, deformation. So a stationary fluid must necessarily be completely free of shear stress. Please try to understand. The fluid cannot withstand shear stress without moving. So a stationary fluid must necessarily be completely free of shear stresses sigma ij or sigma xy, sigma xa, that is the yz, like and symmetry of the reverse. So the only stress is the normal stress, and which is nothing referred to as the pressure. Pressure is acting inward, stresses are acting always out, nor outward. That is the so when that is the sigma and normal stress, which is a compressive as it should be, since fluid cannot withstand the tension. So fluid cannot withstand the tension. So note for the fluid in motion, the normal stress is different on each phase and not equal to the P. When it is in motion, here we are talking about the stationary. That's why sometimes this is the analysis of the hydrostatic pressure. When we should go in the kinematic chapter, then we will again discuss these things, that is the sigma, p, t, tau, all these things details we have to study in the Navier-Stokes equations. That is the there are three conservation equations in the fluid mechanics we have to study. First two is very important. First one is the continuity equations. In continuity equations in one dimension, that is very easy, but continuity equation in three dimension, that is the important. And we are interested the continuity equations in three dimension and then applying the some assumption, or for the special rule we can also write the continuity equations for the one dimension. Similarly, the momentum equations for the fluid element we have to study. I will teach you some, that is the higher, that is the Navier-Stokes equation. And in there I can show you how sigma xx and p and tau xy and tau yx are acting and what is the effect with the acceleration. So here hydrostatic. So in the hydrostatic, the fluid is a stationary. A stationary, so only the normal stresses are acting and pressure is acting due to that is the inward and outward. So the when we should convert for the normal stresses, that will become minor. Here that is the for hydrostatic relation. So fluid element experiences a force on it as a result of the fluid pressure distribution if it varies spatially, means along x-axis, along y-axis, along z-axis. If it is a two-dimension, then we should take that is the only two faces. So consider the net force in the x direction due to the pressure Here, see, this is the fluid element is shown, and first we are considering the forces acting on the fluid element left and right. That's why it is a subsuffix is mark X. So left side, right side, both are that is the written left side, that is the acting P acting along the x-axis. Axis is also marked by the length of the element dx, dy. Here y-axis is the upward, z is the incline. So here that is the mutually perpendicular x, y, z. Accordingly, length dx, dz, dy. Here vertical direction is the y. So left side, you should always that is have some query why we are always taking left side, because left side is the positive and our axis move from left to right and right to left is negative and reverse flow. This is the general some tradition, some trend. It is not necessarily, but for the axis we are generally that is axis is compulsory taking right side is the plus, upward is the plus. This is the general concept, but it is not always compulsory. Maybe sometimes mention you should take the downward positive of the axis, no problem. But here we have chosen a normal case. So left side force is pressure into dy area. On this face it is acting. Due to the length of the fluid element dx. Always remember the partial form due to the effect of the space in that direction. We are writing the right side due to the length of the dx. So p plus del py del x into dx plus higher order term, which we have neglected or truncated. That's why generally books are used to write only two terms, but it is not actually correct. Higher terms are also you may write and give truncated. We have truncated the higher order term. That's all. Because the dx, next term is the d2 py dx dx square into dx ka whole square divided by factorial 2. Let us suppose the fluid element length is 0.2 mm and a square of this that will become 0.04. 0.04, it is still a smaller. That's why we are neglecting. Higher term is again less. Point, 0.2 into 0.2 into 0.2, that will become 8 into 10 to power minus 3. So these that will become very very small. That's why we are used to neglect or cancel it, and generally books are used this two term only, p plus del py del x or sigma if available. Only direction will change, outward inward, but matrix that is the Taylor series apply, that is the same thing. Here that will become that is the sigma plus del sigma by del x into dx. So here p plus del py del x into dx and into area on which surface this pressure is acting, that is the dy dz. That is the important. Similarly, you can write for the y direction, that will become del py del y into dy. So see, all these are mathematically why which we use to present or write. So net force acting along the x-axis due to this fluid element, due to this control volume of the volume is dx dy dj. So summation of forces along this, that is the acting right side plus left side minus, this will become the net pressure force minus del py del x into dx dy dj. Similarly, we can write for y direction, z direction, all will give that is the same style, same system, minus del py del y into dx dy dz. minus del py del z into dx dy dz. So in symmet, that is the matrix form. In the that is the here, that is the vector form, it is represented minus del py, that is the force, net force, minus del py del x I j k, or force per unit volume due to the pressure along the x-axis only is nothing minus del p, minus del p if p is constant. If p that remains constant, resultant force is zero. So this is some idea about the pressures. These all the different situations we have discussed of the hydrostatic pressure. Always remember, not this is the kinematic situations, not that is the we are studying the motion of the fluid element. We have to study. So all these situations I try to show you in this in the term of the stationary pressure in a container of the fluid. Then its measurements. So that is the fluid mechanics instrument. There are so many instruments. Some of them you might be read. Just I will show you and some refresh you. Am I right? So here that is the some barometer. Barometer. Here that is the pressure of this, that is the tube or column, plus gamma of the mercury into H, that is the P atmospheric. And P atmospheric is rho GH, gamma equal to nothing, rho GH. When vapor pressure of mercury nearly zero, or height of the column in the mercury situation is only 76 centimeters. So P atmospheric, that will become 101. Applying that is a rho into G, 13.6 of the mercury, that is the density, and 101 kilo Pascal approximately, or something point that is. So P atmospheric is relative to the absolute zero, absolute pressure, P atmosphere location, and considering why water barometer is impractical. See, if you should use, then it requires 1033 centimeter long of the hour, that is the tube. In case of the mercury, we are using only 76 for the same situations. That's why in that is the manometer. Manometer may be differential, may be inverted. The measuring fluid, that is the we are measuring the pressure difference of the different fluids, or measuring fluid density and measuring the pressure of the fluid pressure is different. So we are always taking high density fluid as compared to the measuring fluid pressure. Here, piezometer, just I have shown you piezometric head, piezometric pressure. This is a pipe and a tube is inserted, hardly that is the 1 mm diameter or less, very, then it will rise H. And this is the manometric, that is the piezometric head, and this, that is could correct using this. Then manometer, this, that is the manometer. one question generally asked from the manometer. So manometers are devices that use liquid columns for measuring differences in pressures. Differences in pressure. General procedure may be as to start at one end of the meniscus if in the circuit is continuous and write the pressure in appropriate unit means in the same unit of add to this the change in pressure from the meniscus of the column and continue when gauge is related to the pressure. So see here just see there is a manometer is shown. This is the a manometer that's nothing but a U type of the tube and there are two ends. One end that is connected where point A it is a mark and right side is the open to the atmosphere and we have to measure the pressure of this container A and right side that is there are two ends. One end is connected to the container which we have to measure the pressure and one end is the open to the atmosphere. Up see here the position of the fluid, that is the position of the fluid inside the manometer is marked. Here is the given. Is it correct? It is a visualized. Now let us say we have to measure the pressure difference of the fluid having density rho, having the density rho. Then measuring fluid devices manometer having the fluid the density greater than of the rho. So we should use the rho 2 density of the fluid having high as compared to the rho 1. So this is the position. Then we are interested. So say first you should take any line where that is the in a line of that is the mark at there that line give a same pressure in the both ends, same pressure at the both end. So we will take a line passing through the Z1 P1 and the right side. It take a line or I will show in the more problem then I can convince you. It correct? So see here first we will take a line and in the passing through the both ends and that line represent same pressure at the both end. This is the simple funda. You can take a line and passing through the both ends, the horizontal line, and at that point in the both end pressures are equal. But that's all. So let us suppose we in this equation we can see left side first we will take left side that is the at mark Z1 P1. So there is a pressure Z1 is the here is the given. So rho G Z1. Is it correct? Rho G Z1 plus PA. What is the PA? Or some height that is the ZA PA plus rho 1 G and P1. All these are the acting. Right side, here is the acting. This difference that is the acting. Right side, atmospheric pressure P1 plus difference of the height into rho 2 into G. In this situation, right side we will take G and rearranging here that is the given. The same thing you just see. Left side that is the transfer the left side term minus to the right side. Then it will become simple. PA pressure of the container which we have to find out plus the pressure acting at the, that is the our Z1. So here see, plus ZA equal to the this height rho 2g Z2 Z1 plus atmospheric pressure. So this is the one use of the manometer. Another see, manometer is connected to the pressure of a flow of the fluid through a pipe. This by first by the, for the container we are interested to find out pressure with the help of the manometer. Second one, through flow through the pipe we have to measure, that is the pressure. So manometer is connected, and here that is the, it is always considering the distance from the center of the pipe. अब see here, that is the important, the line at 3 here mark 3 2, this is the line at which pressure both side is constant. Always remember we, what I told you, okay, draw a line which cuts the both limbs or both side of the tube of the manometer and both end having same pressure. So pressure at 3 equal to the pressure at 2. Pressure at 2 equal to the pressure at 3. And what is the pressure at 3? What is the region? You have to write. So see, the P1 here, see, P1 means pressure at acting 1 plus height of the column del H. So del H, so P atmospheric plus gamma into rho H. This is the acting right side. And left side is acting pressure at 4, which we have to measure, plus height of the column. Height of the column, that is the here L, not 1, L. So right side which we have to measure the fluid having the gamma, and the measuring fluid, that is the manometer fluid is gamma m, means rho m g. G is both side same. When you should rearrange, then it will write P1 plus gamma 1 plus G rho H minus gamma L equal to the P4. This is the pressure at the center of the pipe flowing through which fluid is passing. Again, I am repeating how we have calculated. As I told you, we should take a line at such a point where some informations are available. So in the at point 3, it is the 3 here is the mark of the manometer fluid, and right side is at point 1. So at point 3 and point 3 2 in a line, in a, that is the horizontal line. So pressure at point 3 is equal to the pressure at point 2, or pressure of the, at the point 3 of the tube equal to the pressure at the point 2 of the tube. What is the pressure at the point 2? That is the question arise. So this is the atmospheric pressure, or P1 acting at the P1 pressure, that is the P1, nothing but the P atmospheric plus height of the column rho GH, P equal to rho GH also. So P rho G for the manometer fluid is marked gamma m into del H. Height of the column is del H, right side, equal to left side pressure at P is nothing, pressure at 4 which we have to measure P4 plus height of the column 3 to 4 is L into rho G. This is the length L, and simply rho G is marked by the gamma. So P1 plus gamma m del H equal to the P4 plus gamma L. That's all. Or you can say that P1 plus rho m g del H equal to the P4 plus rho g L. That's all. Our interest to find out P4. So P4 equal to the rho m del Hg minus rho g L, and it is written in a specific volume of the manometer fluid. And yes, a specific fluid of the flowing fluid which through the pipe which we have to measure the pressure, and into L, not the one. It is not one, that is the L. For a gases, the passing through, that is the fluid, it a specific weight is very less as compared to the manometer fluid of the specific. So P4 equals, so in gas, that is the gas compressed, del P in the liquid determine P4 in the pipe. Then differential manometer. A differential manometer determines the difference in pressure at 2 points when the actual pressure at any point in the system cannot be determined. Here see, we have shown that the manometer measures the pressure of a container passing through the pipe, and pressure difference at the passing pressure difference between the 2 points in a pipe. If there is some source sink in between them, or change in the dia in the pipe, then pressure difference will create, otherwise same. So within point 1 and 2, some, that is the source, sink or some obstacle may be provided, they may be changed. So here, this is the one example for the inclined plane is marked here. See, so this is the shown in the difference in piezometric head in the both sides. Just you have to take nothing, any point that is the A and right side, and write down the pressure acting at point A, and same line at the right, and rearrange, and this will come out. It's correct. So manometer, or when we will use more number of the manometer, or you should use that is the inverted, that is the reverse, that is the reverse of the U tube. But principles are same. We can connect more than one manometer in, that is the series also, and applied the formula. Is it correct? You may also use in, that is the these bottom tube type gauge, manometer, digital. These are the you might be used in the lab, in, but in, that is the manometer principle generally in a lab is keeping it in our lab, also in heat transfer lab, fluid mechanics lab, manometers are available. That is a U tube type. In turbine, also manometers are, that is the connected. Am I right? So we will take some examples of the manometer and try to show you how we can calculate the pressure in different situations by applying these methods. So this is the all about the pressure. I try to give something. If you have any query, then ask me. So first lesson today I have sent the notes which I have discussed. Problems I try to, that is the solve in the class, values are given. In the next class means tomorrow we will take some example of the manometers that clarify you how you can take pressure at a reference line or any line that give the same pressure both sides. If you have any query, then ask me, and in the next class we will take the attendance. Am I right? You don't worry about the.
Excuse me, sir.
Yes, yes, bolo. Yes, tell me.
Sir, can you send this PDF also?
Yes, yes. Let us see. Again, I am telling whatever I will teach you, I will send you. Don't worry about these things. But my note is not sufficient. These are the some guideline, important information. You may also go through the some textbook that will help you for the engineering services, gate examination, or for any competition. Some things, sometimes some silly points, some small point maybe I miss not I have discussed in the class, or maybe discuss or not discuss. So that's why I'm again advise all of you, you must go through the some textbook, because this is your very basic subject. Numerical example I try to take and solve in the class, and you also cooperate me, then I will solve more problem. Just you can listen here, that will not help. Today I have sent the PDF the last class. All of you got it? Okay, he may send you. Is it correct? CR will send you. Don't worry. So I will send what I will discuss in the class. I will send, and you go also visit the site which I have given. Anybody have visited or not till now? Just you go and see that is the book. Which type of the books are available there? And Fox and McDonald, you may that is the download from the net. It is available in the net. Because we will take the example, we will give the examination, generally follow this book. Okay, thank you. Or any more query? Okay,
Thank you, sir.
thank you, thank you.